Maybe a short introduction. Dr. Gau received his master's degree from Delft University of Technology in the Netherlands and the PhD degree from Eindhoven University of Technology, also in the Netherlands. From 2008 to 2012, he did a research project in Philips Global Research Headquarters in Eindhoven. He was with NXP Semiconductors in different positions as RF designer, as European Marie Curie researcher, and technical consultant in Delft, Stockholm, and Eindhoven. Since 2015, Dr. Gau took assistant professor position at Eindhoven University of Technology in the Netherlands. And now Dr. Gau is a staff scientist in the research units that we have already heard before of millimeter wave technologies at Silicon Austria Labs Linz. Dr. Gau, thank you very much for your presentation. The stage is yours.
Thank you. Thank you for the introduction, and it's quite a pleasure to give a talk in the university here. After the grant, introducing of the cell, especially the Linz millimeter wave activities, it's my honor to actually to present some of the work in the millimeter field that we did years. So today I'm going to do a lecture with the content of the millimeter wave wireless sensing. So today I'm going to talk about the sensing in different ways. One is active sensing, another is actually the passive sensing. Because the sensing, that means you try to use a millimeter wave to detect an object or know the property of an object. But in this actual definition of the sensing, it did not define that it's in the active way or in the passive way. In the active way, that means, okay, you transfer a signal to an object. Object could use some of the method to get the signal and do the local signal processing, then transfer the signal back to the base station. So that is active sensing. Or in the passive sensing, for example, for the radar signal, you just transfer the signal directly to the object, then you listen to the echo. Through the reflected signal, then you're going to know the property of the objects. So that's why I separate today the lecture. First I will talk about why we want to do the millimeter wave, actually, this frequency sensing, and later on I move to the wireless powered IoT. And because for the IoT, then we definitely have to talk about ultra low power radio in that topic. Then later on, I will talk a little bit on the radar sensing. I hope I will keep the time on time. So first, I will introduce the spectrum. This is the document from the FCC for the whole spectrum allocation. As you can notice, from the right bottom, the corner, the spectrum is very crowded. That is low frequency. If we move to the left direction, go to the left up, I mean from the lowest stage to the second or the third, then you're going to notice so if we from this point and go to this direction, all the spectrum density after this region, then spectrum get to, you started to have some large bandwidth in here. And some of the spectrum is not allocated for the normal people use. That is okay for our daily radio application. So for example, for the military that have special regulation, use the spectrums. So if we look at the normal our frequency range, this is actually the spectrum scanner that my student we did years ago, and we just open our spectral analyzer and we try to monitor the spectrum in the ear. You're going to realize actually even in this commercial frequency range, some of the frequency band are quite busy. For example, in this frequency band, it's quite busy, but its neighborhood is quite silent. And okay, some of the frequency is used again. So that means, okay, not all the frequency is well allocated, and especially in the low frequency band, some of the frequency are super crowded and some frequency are super clean. The clean is for several purposes. Maybe it's actually for the allocation of the, as we mentioned before, the special purpose, for example, for the police or military. Some is because of the frequency is not worldwide allocated. For example, some of frequency could be used in Europe, some frequency could not be used in Europe, only can be used in the US or in the China, in the Asia. So that's roughly is a problem in the low frequency range. The bandwidth is always limited. Because from the channel series, we know if you want to increase the data rate, the first thing you want to do, or most simple way you want to do, is increase the bandwidth. Because, okay, that's defined by the theory. The signal to noise ratio can be increased directly if you increase the bandwidth without doing anything. But if you look at the frequency band, that in the sub-6 GHz, the total unlicensed fixed band for mobile and for other applications is quite limited. But if we go a little bit higher, we go to licensed microwave band. Okay, the bandwidth is a little bit larger, or the free space is larger, but it's not stopped. If we go to the millimeter wave band, there is licensed and unlicensed band. Because our unlicensed band, that's what we call it ISM band. In the millimeter wave, the licensed and unlicensed band in total, they are roughly around 20 gigahertz. But now, actually, beyond these graphics, the people nowadays, we are talking about the hundreds of gigahertz, the sub-THz definition. For example, now in the FCC just defined actually roughly 20 gigahertz for the sub-THz for free. So in that case, it can move the frequency from this range, I mean the central frequency, from this range, go to the traditional microwave band, you already get the benefit of more than 10 times larger of the bandwidth freely. But if you go higher, then you can use more. That's the benefit that we go to the millimeter wave frequency band. Of course, if you have the benefit, there's something you have to pay. First, it is a difficulty. And later on is whether, okay, the product will have more power consumption. And also its frequency coverage. Because we also happen to know with frequency go higher, the free space loss is also higher. So that is something when you jump from this frequency band to the millimeter frequency band, you have to face with. So first, I will talk about the millimeter wave wireless powered IoT device. First is the scenario. Why we talk about this scenario, and is that true? The scenario will be in our life. That story should be started from the 5G, the 5th generation mobile communication, especially in the North America market, because North America market, the most dominant 5G frequency band is on the millimeter frequency. But for example, the 28 gigahertz and the 39 gigahertz frequency band. For the US or for the Asia, there are, for the European as well, they also have another 5G band that is sub-6 gigahertz frequency band that is not on our map today for today's lecture. Because for the millimeter wave, the small cell or micro cell, that application or that scenario introduced a very important part in our life is where you want to put such a micro cell or small cell. If you fly to the San Francisco, you will be surprised to see in the street, a lot of the street light is replaced by nowadays they call it the smart, intelligent street light. So what is a smart street light? That actually is they put a 5G base station on the street light. because in the millimeter frequency band, the signal propagation is roughly line of sight. So if you want to cover, for example, this is the street. If you want to cover the service in this street, you prefer to put a base station maybe on the street light here, just on the cross of the two streets. So that can give you the maximum coverage. So if you have that 5G micro or base station on the street light, especially in the millimeter frequency band, that can bring a new area for us. So it can bring a lot of smart functions to us, because in the millimeter frequency band, you can achieve the tracking, the object tracking, by using the beamforming function of the base station. That means, okay, the localization could be easily done. Not just increase the data rate for our mobile phone, it also can achieve quite a lot of the accurate localization service as well. So if we go to the indoor scenario, because now also the mobile provider also provide a scenario that you can rent a device at home. So from the 5G base station, you first connect it to a unit at home. Then okay, the device at home, the PCU at home. Then okay, distributed the signal again indoor. So that means it's possible that also we connect the smart building sensors and smart building anything into the 5G scenario. In that scenario, the smart parking sensor, the bus tracking, a lot of the new service can bring and improve our life. If we talk about the millimeter band, first thing I think maybe pop up into your mind is, okay, what's a wavelength? The wavelength is quite small. That's why we defined its millimeter frequency band. And it gave us an advantage of that frequency band is antenna. Now, if you open your mobile phone, or okay, if you see the FM radio, you will find a very big antenna. So in the millimeter band, especially on the 60 GHz frequency band, the antenna size could be just of several hundreds of micrometer size. So if we look at the size compared to the traditional FM radio, the antenna size, I think it shrinked hundreds of times smaller. So that means, okay, on a single piece of the die, you can integrate it, the active component, I mean the RF transceiver, together with on-chip antenna. So that means you can integrate it, the SOC, the RF front end, the basic baseband, the signal processing together with antenna together. So that could achieve a very elegant monolithic, fully integrated IoT device. Also, as we will discuss later, the wide bandwidth available in the millimeter frequency band also can increase the energy efficiency. Here is energy efficiency is energy per bit, because energy consumption is for the customer, for example, for the mobile phone. As a customer, you will pay attention to the mobile phone. How long is the battery last? But actually, when you want to evaluate the energy efficiency, we want to use energy per bit to evaluate, because in the meantime, how much of the battery consumed and how much of the data you transferred, then we average the energy to every bit. Then you can evaluate how good is energy efficiency in certain frequency. Also, because your data rate is your speed and the data rate is quite good in this frequency. That means if just a short message, for example, if you want to just transfer a file with a megabit size, it can be finished in just a short transfer burst. Not like in 10 years ago in the internet, you have to download a file maybe half an hour. But now in the millimeter band, you can achieve actually everything in a short burst. That means, okay, the energy, total energy consumption, energy per minute integrated with a certain time period. If we, in that calculation, you can figure out the millimeter band also can achieve very high efficiency through the short transfer burst. So that bring to our system architecture. That means, okay, in the millimeter frequency, the IoT network, that means, okay, still a base station transfer to the signal to the sensor node. But the sensor node and the base station could be different than the traditional sensor node and traditional base station. First, the size of base station can be very small. If we calculate it well, the base station micro cell or pico cell of the indoor in-home use could be quite small, just a box size. I mean, the box is when you buy the mobile phone, there is a box. That is a box size, not a big box. It's really a small box size. And that box size could be integrated with a phased array function. So not just one antenna, it can be an antenna array integrated in that base station already. That means with that base station for indoor application, you already can have the tracking function. For the sensor node, also different than the traditional sensor. It could be integrated everything together, including the antenna. That means, okay, if we can include as more component as possible into the silicon, you can decrease the price of the final product quite a lot. That means for the integration level can be much higher. Maybe you will not see a separate antenna. You will see the antenna through the antenna on chip or antenna in package solution. So you just see a black dot on a board, maybe. You will not see the big antenna anymore. Also, that means, okay, the whole system will be unbalanced, and also that is matched with nowadays the edge computing concept. Because, okay, that means so the base station can have more functions and the sensor node are more smarter. And a lot of sensing function can be shifted to the sensor node, and the power consumption is low, and the base station for indoor application have to be more intelligent. And it's also possible can dream of the passive wake-up node already. That means the sensor node without the battery can be powered up by the power transfer through the base station to the sensor node. So that really opened some of the new door to earth. If we want to continue that story, then first we want to discuss, okay, where is the most dominant component that consumes the energy, and how we can calculate the energy, and how much of the bits that possible can transfer through that energy. So here we just show power transfer link and uplink with the data transfer. So as I mentioned before, the downlink is power transfer link. So the power is transferred through the base station to the antenna, then antenna transfer the energy to the energy receiver component. The energy receiving component generates the DC energy, then the DC energy going to store into a storage unit. That could be an on-chip capacitor array or supercapacitors through the trench, deep trench integration of those kind of new technology, or it's just off-chip energy storage unit. But that's not the key point. The key point is you have to have something to store the energy. So after store the energy, after some processing, the transfer the signal through the antenna, then back to the base station. So the most important thing in this total transfer link is firstly the antenna gain. on the base station. So what's the dBi of it? Then we move to the antenna of the receiver, because that could be linked to our previous discussed antenna on chip or antenna in package. Because antenna in package, antenna on chip could introduce different efficiency with different antenna gain and directivity. So that means, okay, here you have to choose. We're going to discuss, we have to talk, okay, what is the best choice? And for the antenna interface to the wireless power receiver, the impedance is definitely not the same, so going to have the matching network. If it's the antenna on chip, then the matching network definitely will be different compared to the antenna in package. So that passive network will generate the first loss. The wireless power receiver will generate the second loss term, but compared with matching network, the dominant of the loss of energy definitely from wireless power receiver. For the energy storage unit, then I have to think about the leakage. That also including to the your active component leakage and energy storage unit leakage. So whether your active component can be affordable with that leakage, or is some way to decrease the leakage. And every time when you actually turn on and turn off the circuit, it will also generate some efficiency discussion. For the transmitter, for sure, okay, transmitter efficiency will actually bring to the discussion, because what is the modulation type is optimize the situation for this kind of scenario, and what's the best frequency range. No matter to discuss the transmitter antenna efficiency and the type and the propagation loss on the uplink. So with those parameters, we can have a first mathematic of the downlink. The downlink is first composed of the power transfer from base station, antenna gain, and also the received signal, the received antenna gain, the efficiency of matching network, rectifier, switch, and the data transfer link is how much of the data transfer link related to the data power, the transmitter signal loss, and everything need to be transferred into the signal to noise ratio. But in the downlink, we have to mention, because, okay, as we mentioned before, because the total energy is stored into the capacitor, that means you have to do the integrating the time domain. So you have to multiply by the time, okay, how much energy you stored. After the basic introduction, I guess you're going to ask me, okay, what kind of the energy you can receive nowadays, and what kind of data now we can transmit it nowadays as a millimeter frequency band? Is that just a beautiful story? So here I gave some estimation about the transmitted power is 20 dBm, and antenna gain is 20 dBi, and received antenna on the chip is 0 dBi, and the charging time roughly 10 seconds. Also for the uplink, for the data transfer, it's going to have 10 nanoseconds of the data transfer time. In that calculation, the energy actually, you can receive quite decent energy in the 1 meter range. And also in the 1 meter, actually, in the uplink, the power is also affordable to transfer some data. So roughly, I remember the data that we can transfer already is roughly close to the 2 words nowadays. That means, okay, in the short distance, with the short burst, in the 1 meter, you can achieve actually at least 10 bit transfer already. Then you will discuss with me, I guess, the wireless power transfer techniques. So what kind of the wireless power transfer techniques are available in the market, and what is actually the power transfer techniques nowadays we could be used. And also in that discussion, we have to link to the IoT device size and the power level. First, I want to introduce the different of the wireless power transfer techniques. Those are in the market, those have the inductive coupling power transfer techniques, the resonant inductive coupling technique, the capacitor coupling techniques, and the electric magnetic coupling techniques. By the name, you can already start understand the transfer distance. The inductive couplings is by actually you put the two coils actually close to each other. Then, okay, through inductive coupling, the energy can transfer from one coil to another coil. The resonant inductive coupling is different than the inductive because if you tune the two coils at the same frequency band, then okay, it can enhance the coupling efficiency. For the capacitor coupling, you just to put two metal plates together, and the energy can transfer through the electric field. So inductive coupling is through the magnetic field, and the enhanced inductive coupling is also through magnetic field, and the capacitive coupling is through the electric field. But electric magnetic coupling is from electromagnetic field. That means that by definition, it can go a large distance. So that is actually can give you first first understanding of the wireless power transfer distance. If we link to our previous discussed the 5G or millimeter wave band, that means if you want to have a longer communication distance or power transfer distance, electric magnetic field coupling is the best way. That means you need to have an antenna. So if you want to do the antenna communication, that means that the antenna will be a bottleneck for the size. So that's going to have a different level of the IoT size, millimeter size or centimeter size, also that related to the frequency range. If in the millimeter frequency band, now the IoT device could be very small in the millimeter size. The power consumption level is also related to the frequency and the power transfer efficiency. In the millimeter frequency band, as we talked before, because the power consumption of power conversion efficiency is limited, so the power might be limited. But okay, you can give more time to do the charging. For the inductive coupling and the capacitive coupling, the energy level can be quite high, but as I mentioned before, okay, that limits the distance. Since we talked so much of the wireless power receiver, so what is the circuit to do this function and how we achieve that function? So then we're going to talk about the wireless power receiver, the architecture. Wireless power receiver could be achieved through the rectifier. Rectifier is just putting a very simple rectifier is half bridge rectifier. So it's a diode connected with a load. Or can go to the full bridge rectifier, and the DC voltage can be generated for the load. Or if you want to have the higher output voltage, because in the half bridge rectifier and the full bridge rectifier, the output voltage is roughly in the same order of the signal amplitude. But if we imagine the output voltage, if you want to be higher than the amplitude of signal, then you want to cascade them together. So then you're going to use a multi-stage rectifier or Dixon structure. In the Dixon structure, by cascade different stages together, you can have n times of the amplitude of the signal. Although we draw the diode in this graphics, but it can be implemented as a diode connected transistor, or you can use a Schottky diode to implement those diodes on the silicon. If you have later on when you have the wireless power receiver, it will be interesting for us to discuss, okay, how you want to transfer the power in which time sequence. For example, if you want to transfer the energy all the time, or if you want to transfer the energy in different time slots. So that generally gave us two types of systems, the duplex system architecture or sequential system architecture. In this architecture, the energy is consumed directly by the active component, and the rectifier in that architecture have to be optimized for the highest efficiency, because you have to receive the energy directly and provide energy immediately for the active component. But for the sequential system, the energy can be stored into the energy storage unit. That means you can use the time to compensate for the efficiency. In that case, you would like to optimize your wireless power receiver to the direction of high sensitivity for longer wireless power transfer distance. So you could have separate time slot for power and data transfer. So in this way, you can introduce the three parameters in the time domain to optimize for the data transfer, for the power transfer separately. Since we are scientists, we do everything scientifically. So how is a modeling part of the wireless power receiver? As we discussed before, in the architectural page, the system could be optimized for the efficiency, and system also can be optimized for the sensitivity. What's the difference in between? That's related to a concept of the small signal region. Because if actually in the small signal region, the transistor is pushing to the substrate of the region, and using the square law to describe the diode is not enough. So that means, okay, we have to use a different way to describe it. Basically, you have to treat the transistor as a diode, and using the Taylor expansion of the cell equation to open the current and voltage relationship. And also a key component we noticed is actually the parallel resistor with a diode that generates quite a big loss of the diode. So here is a plot with and without the diode. Without the diode, the circuit loss is much lower than what we predicted, and it's also quite different than what we measured, because that's from the textbook. It's mentioned only using actually the diode model to describe diode. But later on during the measurement, we figure out that the two curves not matched. Then we realize for any diode in the silicon, they're also in parallel resistivity part, and that part introduced quite a big loss. So by introducing a parallel resistivity part, you can match well with measurement data and the modeling part. Also, you will be curious for the Taylor expansion by cell equation, which is actually more suitable for this application. That's also related to a concept of time variant input resistance. Because wireless power receiver, your signal level also is small, but voltage swing is large. So that means your input impedance is changed also dramatically. And as we discussed before, there is a resistance part actually to the dominant influence. So we figure out the Taylor expansion and Bessel equation do have the difference. And using our previous introduced resistance model with Taylor expansion and Bessel expansion, we realize, okay, the Bessel equation could fit much better than the Taylor one. If the input power goes to a large power domain, I mean, okay, the power is pushing the transistor can fully on and fully off, then we can simplify the equation quite a lot with only using traditional square law equation to describe the transistor. That's enough. Those are the equations for the turn on current and transistor introduced the voltage drop. And in the turn off period, the leakage current it cannot be ignored. And also the voltage drop during the turn off period is also cannot be ignored. The loss is composed of the saturation region loss and leakage current introduced loss. That means in the time domain, this region introduces a saturation period loss, and the leakage in this region introduces loss. By multiply the current during the turn-on period and the voltage drop this period, we got the loss of during the saturation region. And the leakage current multiplied by the voltage drop during the turn-off period, get the leakage power consumption. After a while, we figure out a very interesting scenario. Actually, for the wireless power receiver, there are different specifications of load current. But if you optimize each circuit well, they can reach the same efficiency quite good. Also, that can be predicted by the theory. So that means in the design flow, you first want to estimate what your input voltage swing and what is your output current. Based on that estimation, you want to optimize your wide transistor wide and length ratio to optimize the circuit to the peak efficiency. But there are some points we want to also mention. If you optimize your transistor size, you're going to also distinguish the transistor functional on the different point for the efficiency and output voltage. For example, if you optimize the transistor on the best efficiency point, and you are not optimize the transistor on the best output voltage point, so in that case, you would like to discuss what is your most important parameters, or what system architecture you're going to use. Somehow you will notice the optimized the transistor size, optimized efficiency point, you cannot find the optimized threshold voltage. That's normal, because if your transistor threshold voltage is low, then you can have actually higher current, but you introduced more leakage. So from the theoretically and experiment, that means you want to have some body bias. Through the body bias, you can change the threshold voltage of the transistor. So you can optimize the leakage part and the forward voltage power drop. How is the performance of the wireless power receiver performance in the millimeter frequency band to the traditional I frequency band or millimeter frequency band? So first, the millimeter rectified is quite challenging in the efficiency and the sensitivity, especially if we do the comparison of the efficiency is quite is lower than in the traditional I frequency band. I mean, under sub-6 GHz frequency band. But from 3 years ago, the rectifier efficiency also optimized, actually started the trend of actually beyond the efficiency in lower frequency. That because, okay, we start to optimize the transistor threshold voltage and start to optimize the matching network for the power, for the loss in the power matching. Since we introduced the threshold voltage, then okay, I'm going to talk about threshold voltage modulation techniques. In a diode connected way of the transistor, there is a parasitic diode that could dominate the loss as input. That is the diode of the body and the drain. In the positive phase, this diode is also on. That means, okay, the parasitic body to drain diode can cause a short circuit. And it also can introduce some small leakage. So if we just short connected this diode by connecting the body to the drain to the same voltage node, then we can short this diode. In this way, we can increase efficiency quite a lot by decreasing the leakage current and increasing the forward current. But of course, in a certain voltage swing, that's also a design parameter. Since it's a diode, then the turn-on voltage is quite important because it's related directly to the VGS minus VTH. So if you want to decrease your transistor resistivity, the channel resistivity part, then you want actually higher the overdrive voltage. In that way, you want to have a higher VGS minus VTH. But if you, in a simple diode connected way, your drain and the gate are connected together, then you have no freedom to optimize it because they are fixed and they are equal. So if we separate the drain voltage from the gate voltage by inserting an inductor and through the series resonant theory, and we boost the voltage swing at the gate, then we can introduce another parameter of the Q into the overdrive voltage. That means, okay, you can increase the voltage swing. Then you can decrease the loss of the transistor. In that way, you increase the efficiency. But also that means, okay, your voltage swing is large and some signal will actually coupling to the output directly through the parasitic capacitor of the between the gate and the source. So since we start talking about signal feed through, then how about adding an output filter? If at the output we put all filter and filtered out the high frequency component, only left the DC component, then we can definitely improve the efficiency. That's our first guess. Then we tried it. Yes, that is possible. In the output, the frequency feed-through can prevent output high frequency discharge of the storage unit, and that in that way it can increase efficiency. Here we want to mention, because of the forward part, this actually high frequency introduced feed-forward have different phase. Because if the signal is higher than output signal, and the time actually is much smaller than in the negative period. That means, okay, the discharge period is longer than the charging period. So if we optimize the circuit first, the phase in this range, and we put a filter, the efficiency can be improved for sure. So we prove that theory on the silicon, and we put input matching and inductor picked diode stage, also with a self-threshold cancellation method and output filter. The efficiency indeed improved first from the 7% directly to the 15%. And also this structure could be extended to the multi-stage structure. So this is originally first stage, one stage structure. If we put a second stage and also the interstage, then we can borrow the concept from Dixon structure to this topology. Output filter definitely is necessary. So with this topology, the output voltage can be 2.5 times of the amplitude in theory, but in the measurement, it can reach the 2 times, at least 2 times now. If we have the wireless power receiver, yes, we have the wireless power receiver, then we can discuss the node architecture of the IoT device. Because you have the receiver part, you have the transmitter part. That means you can separate the architecture into the two antenna solution or one antenna solution. The difference in between is whether you have the switch or not. As we mentioned before, the switch going to introduce a loss, and this loss going to decrease your efficiency and also make your transmitter efficiency low, and transmitter output power is also. The two antenna on chip solution, you have the two antenna, you don't have the switch. But in this architecture, you have two antenna, and two antenna are located quite close to each other. That will introduce a crosstalk and the coupling in between. That will decrease antenna efficiency. So those two architecture have the advantages and disadvantages. In the node 1, we tried the two on-chip architecture, on-chip antenna solution, and one is for the receiver antenna, one is for the transmitter antenna. And antenna crosstalk can indeed actually decrease transmit power, and also the received efficiency also decreased by the coupling in between. This is the one on chip antenna solution. The switch is inserted in between of the receiver, transmitter, and the antenna. Also because of the switch gonna to connect to the three component, switch itself also have some isolation point worth to be discussed. In this work, we successfully achieved the dual frequency, and the efficiency of the sensor node is kept at 4% of efficiency. As I mentioned before, all the active components in the IoT, on this type of IoT device, have to be ultra low power. So every function needs to be simplified and for the power consumption. Next, I'm going to introduce the low power radio, because the power consumption is very important for the active component, and whether it's possible to achieve the ultra low power radio with just limited power is a very interesting topic. First, I want to mention the ultra low power radio always deserved to be discussed with energy a bit, because that's a key parameter. And in the system level, there are different parameters should be discussed on a different level, such as in the MAC level, in the network level, and physical level. Even in the circuit level, we have different parameters. For example, the frequency. Here, I just in this graphic, in the right graphic, I list the most dominant parameter of the circuit, such as noise factor, the efficiency, the power consumption, sensitivity for the receiver, and also the demodulation, the signal-to-noise ratio for the demodulation. The first thing popping to your eyes could be the parameter of the F, that's the frequency, because noise factor is related to the frequency. For a given technology, with the frequency go higher, the noise will be higher. And if you do the modeling of the receiver transmitter DC power consumption, you also figured out the power of the DC power consumption is also related to the frequency. With the frequency go higher, the power consumption of the total power consumption of the total power consumption and the total output power not actually go higher. I mean, the TX output power with frequency go higher, okay, limited. And the DC power consumption of transmitter is also actually go higher. Then there are some problems actually when you look at system architecture level. First, the high standby power consumption in the music frequency band. Because if you open a state-of-art product or go to the IEEE website, search for the latest reported data from the transceiver, the power consumption is quite high, but those are the standby power consumption. The reason because the circuit is very complex. Also because you need to meet the modulation requirement in the linearity point of view. Generally speaking, the system architecture is quite complex, and that generates too much of the power for everything. So if we talk about the high standby power consumption, if we want to minimize, it would be worth to think about the duty cycle wake-up receiver and shift to the 2.4 GHz of the knowledge to this frequency band. And if the PLL is very complex circuit, is that possible to use the injection locking oscillator to remove the high power PLL? And whether we can find some power efficient modulation to simplify the power consumption. So generally speaking, in the system level, whether could do some innovation and do some creativity to decrease the power consumption. First, I want to introduce the concept of asynchronous, the duty cycle wake-up scenario. So in this scenario, there is a wake-up radio and there is a main radio. The wake-up radio wake up the main radio, and the wake-up radio could be using the simplified architecture. And the main radio can still using the phase array architecture. It's a main radio for the quality of the signal, but the wake-up radio is only optimized for the low power consumption. the control voltage is the only always-on component is the control voltage. The control voltage controls monitoring the environment and send the control voltage to wake up duty cycle. If the wake up radio pick up the command to turn on the main radio, then the main radio will be on. In that sequence, the power consumption of the system will be optimized well. That means the wake-up radio in the control part should have a high sensitivity and have a wide locking range. Before we move to the next slides, since we already studied the injection locking based receiver topology, if we use injection locking with mixer, we call it self-mixer architecture, then we can generate the envelope of the signal. By detecting the envelope of signal, then the control logic can have the idea of whether there is a signal or not and what the signal looks like. Let's zoom into the self-mixer, this part. The self-mixer is composed of injection and locked oscillator with a passive mixer. Basically, it introduces a signal and injection locking oscillator locked to the input RF signal. So this is the imaging of the RF input signal. Through the second pass, the RF signal can be also connected directly to the mixer. So it's a signal on this node and the image signal on another node of the mixer. So through the self-mixing, it generates the envelope of the signal. It's on and off control signal. So in this architecture, there's no PLL, fixed locked loop. So the power consumption is quite minimized. And the sensitivity in this architecture could be optimized based on tuning the injection locking oscillator tail current. And the locking time also can be optimized in that way. Because for the wake-up radio, the locking time is quite an important parameter. So how is the performance of that architecture? The power consumption of the entire wireless wire front end now is only around 20 megawatt. And so it's quite affordable as a wake-up radio. Here is our silicon presented in a CICC, and the whole power consumption is only 9 millivolts, with output power of the minus 10 dBm, working in the 77 gigahertz range. The locking range is 10 gigahertz. The core part is still the injection locking oscillator, but the injection method. In the injection method, there's two differential buffer for the differential RF signal. And we will use the cascade input buffer to enhance the injection locking oscillator sensitivity. In the measurement, the sensitivity of this injection locking oscillator can reach the minus 60 dBm, and the conversion gain is 10 dB. And the power consumption of everything including the buffer, only 10.2 millivolt. The first graph on the left up corner is a free running spectrum of the oscillator without the signal. When the injection locking oscillator locked to the signal, the phase is changed is improved. This is under the minus 16 dBm injection locking situation. So the phase used from this noise, from the graphic on the right bottom, the compare with unlock situation with lock situation, the phase at 1 megahertz is decreased by the 20 dB. In that concept, if we can connect the injection locking oscillator with a low noise amplifier, with tunable phase shifter, with a passive mixer, we can achieve the ultra low power radio expression on the receiver part in a single die. This is our work integrated together with a low noise amplifier, mixer, and phase shifter injection oscillator in only 640 micrometer by 410 micrometer size of the die. In this single 60 GHz receiver, the input RF signal output already the baseband demodulated signal. And the whole receiver power consumption, including the low noise amplifier, oscillator, mixer, phase shifter, and baseband buffer, is only 16-4 millivolt. So compared with DC power consumption to the other work, this architecture has the potential to achieve much lower power consumption. And it's also possible to transfer a decent data already. In previous two sections, I talked about the active way of the sensing. That means, okay, you transfer the signal to the object, pick up the power or pick up the signal, and the object transfer the signal back to the base station using the transferred the data signal to do the object detection or object analysis. Nowadays, a quite hot application is radar sensing. The radar sensing, by its name, is okay. You transfer a millimeter wave signal to the object. The object reflects the signal back to the base station. By detecting the echo signal, the base station or the radar system can detect the speed and the distance. As I mentioned before, the whole system, the radar system, is based on the ecosystem. And that means, okay, there are some quite important things we need to discuss. First is the Doppler effect. Doppler effect, that means, okay, you transfer a signal to object, and you will receive the radar receiver will receive the signal back, but the received signal will be modulated by the object's moving frequency. So by detecting the frequency difference between the transmitted signal and received signal, you can calculate it back the speed of the object. For example, in the 60 GHz, if the speed of the object in the range of 10 kilometers per hour, that's normal human working speed, to a decent driving speed, 100 kilometers per hour, the delta F, the frequency difference between the transmitted frequency to the received frequency, is in the range of the 1 to 11 kilohertz. So in the radar base station or radar reader, you only need to detect the 1 to 11 kilohertz signal. Based on that signal, you can calculate back the object speed. But I also want to mention the object speed have negative and positive two situations. That means the object go further or go closer. Another way nowadays also very interested in the industry is FMCW radar. The difference of the FMCW radar is the frequency is also changed with time domain. So you transfer a triangle signal. That's a job. And you, by detecting the received signal and transmit signal, so you also still need to detect the frequency difference. And by detecting the frequency difference related to our frequency, then transmit signal frequency, you're going to detect the speed. Another important parameter in this way is, okay, you introduce another sweep time of the frequency. Not just the 2 delta frequency, you have the chirp frequency and also the time of the fly. Then you have a better accuracy on the D, on the distance information. The radar is not just suitable for the car. It can be applied in quite a lot of the commercial products nowadays. For example, for the door, automotive open door. In quite of the scenarios, those doors now using the thermal detection, but for the keys, it's a problem because always that have the distance angle, and sometimes generate the trouble for the keys. So that's a good application scenario for the commercial radar, because that means radar can actually detect well of the human body, no matter you are adult or you are kids. So generally speaking, the standard radar is the radar can be used as a standard component for all the engineers. For example, the UAV applications and automotive guided vehicle, the speed meter in the highway, and the industrial. And in the industry can be used industrial alarm, and also can be using as a switch in the industrial equipment. So what is the radar chip looks like? It's a quite complex system. First, I want to mention. Here I just list architecture of the radar system architecture, and also its die. In the radar system, there is a radar front-end system. There is a transmitter part. Normally, is a PA with a power detector. So the radar system need to know, okay, how much of the power is transmitted. So a power detector is necessary, and the power amplifier on the silicon. As I mentioned before, the signal generation or the frequency synthesizer is to generate the FFCW signal or generate the signal for the radar, for any kind of radar. So it's a very important critical part for the radar component. The receiver part, it normally composed low noise amplifier, a mixer, analog baseband part. Yeah, the baseband part, the bandwidth related to your speed. So normally it's separated into the low bandwidth filter and high bandwidth filter. And also the tunable band. Again, because the tunable gain is to compensate the distance, different distance. Because with different distance, there are different signal level, different power level of signal to the receiver chip. And the baseband have to tune well the signal level, so the ADC can have a good voltage swing in the interface. So if you open such a radar front-end die, you will not be surprised to see the ADC digital front-end, the transmitter chain, the receiver chain, the analog baseband, the local oscillator, distribution network, and the frequency synthesizer. So it's a complex system. How is nowadays modern commercial radar? It works and how accurate it is. Here I just show an example of the object and radar test environment. And the object, the echo level, the echo signal in the range of the minus 58 dBm, the reflected echo signal power level. That means you can have a good signal to noise ratio already. So the idea quite match well with the theory. Also, you can interesting to say, okay, the echo generates the echo itself. So you have different tones. How accurate it is. As we mentioned before, by detecting the different frequency difference, you can calculate back the distance. Here we just do a comparison to the laser and to the radar. And the distance, actually, the difference is not that big. It's quite accurate because now in the 60 gigahertz, you have 7 gigahertz of frequency band. Bandwidth, 7 gigahertz of the bandwidth. So the accuracy is quite okay. Then you're going to ask, if I have two objects, and could you distinguish the difference between the two objects? Yes, we can also distinguish the distance revolution. That's the angle of arrival. So from this measurement, you can see, okay, put two reflectors, and you can distinguish those quite well. Finally, let me conclude my talk today. So first, the medium frequency band have much bandwidth that could actually enable some of new applications. And the power consumption is an issue for the monolithic fully integrated solution. Also for the radar chip is also an issue because otherwise its temperature is too high and the PVT variation is also large. So finally, I have to thank you for joining today's lecture. And if you have any questions, you're all welcome to ask.